Hey, good afternoon. Well, it's actually evening here. So, welcome to Coach Scott's Chemistry again. And guys, you're going to get this worksheet tomorrow. And this is a real challenging top problem. I had to get to it. In fact, I had to think about it because this particular problem, we're going to have to use what we learned in first semester as far as how to balance questions. And we're also going to be working on our stoichiometry. So, let's read it. When a steel cylinder of oxygen with a volume of 14.5 liters was used to supply oxygen to an oxyacetylene torch, the pressure in the cylinder changed from 208 to 201 atmospheres. The temperature of the oxygen was 25 degrees C at the time of both pressure readings. So the question is, how many moles and how many grams of oxygen had been used up? Okay, so there's our equation. All right. It didn't have any of this, so I had to balance it. This is how I did it. All right. I knew I had to have two carbons on this side, so I added two, and that wasn't enough. All right. Well, I had two carbons, and then that gave me, I needed at least H2. So yeah, it ended up, this is how I balanced it. 2 moles of acetylene plus 5 moles of oxygen yields 4 moles of carbon dioxide and 2 moles of water. Okay, and I can balance that for you later if you have any questions, but it works out. How many moles and how many grams of oxygen have been used up? So what we've got to do first is we've got to find out how many moles we had it when we started. All right, so let's set that up, and of course we're going to use PV equal nRT, the ideal gas law. And this first pressure, let's see, it was 208 atmospheres. My first volume, I had a volume of 14.5 liters. That's what it is. All right, and that's the volume of the container, equals N, and that's what we're going to try to find out. The gas constant we're going to use is 0.0821, which is the one we use for atmospheres, and the temperature of the oxygen was 25 degrees C at both times of the readings. So let's go ahead and do that. 25 plus 273, our magic number, 8298. Okay, so that's our Kelvin temperature. So let's see what we get. If we take 209, and let's look at our math, our algebra. Okay, I saw my magic pen I'm using, Sharpie. If I divide through by unity, or 0.821, and I divide through by 298, that's going to cross that out. And if I do it on that side, I got to do it on this side. Normal algebra rules times 298. Okay. Use my calculator. See my fun calculator there? Turn it on, clear it out. So I got 208 atmospheres times 14.5 liters divided by 0.0821 divided by 298. That gives me 123.3 moles. So I'm going to write that in red. N equal 123.3 moles O2. Now we're going to do this in green. My second pressure was 201 atmospheres. Volume is still 14.5 liters because gas will totally take up the space that it occupies. All right, so temperature is the same. We're going to use the same 201 and the same temperature 298. Now let's do the math on that one. 201 times 14.5 divided by 0.0821 by 298. That's going to give me a moles, an N of 119.1 moles. We're going to call that N final. We'll call this one N initial. So if I subtract 123.3 minus 119.1, that's going to give me a delta, okay, N of the number of moles of oxygen we used was 4.2 moles of O2. So that tells me on part 1, my first answer. Now, how many grams of oxygen? Well, I've got my moles. 4.2 moles O2 times 1 mole O2. And if we look at our periodic table, one oxygen atom is 16 grams per mole, but we've got O2, so that's going to be 32 grams per mole, or of O2, excuse me. So I'm going to multiply that times the 4.2 times 32, and that's going to give me 134.4 grams O2. So I've got that part of A answered. Now, how many moles of acetylene were burned? Okay, I've got my stoichiometry there. So I use 4.2 moles of O2. All right, and this is a mole to mole old stoichiometry problem. So let's think. For every 5 moles of O2, we consume 2 moles of acetylene. Okay. From the balanced equation, 5 moles O2, 2 moles acetylene. So what have I got to do here? This is going to cancel out my moles of oxygen, and that's going to give me my moles of acetylene. So this looks like a very tricky problem, but is it? Not really. 4.2, okay, times 2 divided by 5 is going to give me 1.68. He's red. Moles C2H2. So if you recall, what do we call this? This is the mole ratio. And we're just doing exactly what we did on the second quarter. Again, not that hard. So anyway, that's how to do that problem. We'll look at some of these other ones here because I've got some time. So here's one. This is number 5. A steel cylinder with a volume of 25 liters contains nitrogen under a pressure of 148 atmospheres, a temperature of 25 degrees. How many moles of nitrogen does the cylinder contain? PV equal nRT. My P is 148 atmospheres. All right, my volume is 25 liters equals my N. I don't know my N, so we got to find out. My R, we're using atmospheres, so we're going to use 0.821. That'd be atmospheres, liters, moles per Kelvin. All right, and my Kelvin temperature would be 25 plus 273 to convert it, 298 K. Okay. Now, if I multiply that, we're going to be able to cross out some things. Let's go ahead and do that if you want to. Or I would just leave it like it is. All right. I've got that because I'm going to multiply those two together. Just for fun, let's do it. All right. 0.0821 times 298. If I multiply that number I get N, whoa, 2 pens in my hand, N times 24.4658. I'm going to keep the numbers there because we're doing it. And if you look at the unit on that now, I've crossed out my Kelvin temperature. So now I'm just atmospheres times liters over moles, because I've eradicated the Kelvin unit. This is dimensional analysis. Now, if I multiply those two together, I'm not able to eliminate those units at all. But let's see, 148 times 25. All right, I get 3,700. 3,700. See it? 3,700. And I have to keep my units on there. Atmosphere liters equal N times 24.4658 atmospheres liters per mole. So I'm going to have to eradicate those. So I want to divide through by that. I'm going to do it. 24.4658. Use the same units. All right, I do that. If I do it on that side, I got to do it on this side. 24.458. 4.458. 4658. My fault. 4658. Atmospheres liters per mole. So I'm able to eliminate all those units. I take that, divide by 24.468, 4658, and now I get 151.2 moles, and that's my N. I've solved the problem. Oh, let me move that down a little bit so you can see what I did. See what I did? Not hard, guys. Y'all have got this. So that's the ideal gas law. There's some examples, and you'll get this worksheet tomorrow. You've got it. Work it. Life is grand. Okay, until next time, Coach Scott saying, see you later.